All right. I think the attendees have sort of come together. So, welcome to this webinar. We are here today to talk about MRV. I'll give you a brief introduction to the agenda. We'll start with a couple of speaker introductions, and I'll be following that with a brief overview of our database that sort of marks the motivation for this call today before handing it over to our lovely speakers, who will share some project insights. Following that, we'll do a Q&A. We're hoping for having about half the time of this call for that Q&A. Please feel free to ask your questions at any point and drop them into the Q&A function, and we'll answer them at the end of the presentations. And towards the end, we'll share a couple more next steps and opportunities around this database. So, who are you seeing on the screen? I'm Anna Madlener, Senior Manager for MRV at the Carbon2C initiative. Carbon2C is a nonprofit organization funding the evaluation of ocean alkalinity enhancements, efficacy, and safety as a climate solution. And I'm very excited to welcome 5 fantastic speakers today who have been in the weeds of answering those real-world questions or those questions in real-world OAE applications. We'll be moving the presentation sort of from open ocean towards the estuary application. So Dr. Adam Subash will kick things off. He's an associate scientist at the Woods Hole Oceanographic Institution, followed by Dr. Steve Romaniello, Director of Geochemistry at Vesta, handing it over to Dr. Mallory Ringham, who's the Head of Ocean Science at Deb Carbon, then Dr. Will Burt, the VP of Science and Product at Planetary, and lastly, we'll hear from Dr. Jamie Poulter, Associate Professor of Oceanography at the University of Rhode Island. My colleague Danny will add a bit more information on all of these folks and their projects in the chat now. Before handing it over, I want to very briefly give you an idea of the database that sort of sits at the core of this call. I am not going to flash it or open it up just to keep things focused, but Danny will drop a link in the chat. The motivation for this database was really that we at Carbon2C had often been asked in the past about how OAE field trials should be monitoring, what parameters should be included, and it felt like we wanted a one-stop shop sort of that documents what all of these amazing projects have been actually doing in the field. And so the goals of the database are to provide a resource to navigate different monitoring plans and measurement tools, document learning and changes over time, and illustrate complexity and areas of convergence today. Importantly, what the database does not aim to do is compare or evaluate projects' safety or efficacy. On the screenshot here, you'll see a glimpse of what's included. So that includes also, for example, a parameter overview and sensor overviews. One thing I do want to highlight is the key metric that is reported in the database and that you'll see on the slides of the presenters today. Everything that we have sort of reported in the database represents the measurement share. So this is for any given category that is of interest in the moment, the number of unique measurement points for a category, such as a parameter, purpose, or a combination of those, compared to the overall number of project points at a given project. So as such, it demonstrates sort of a prioritization within each project rather than a comparison of raw measurement counts between these projects. And when there's an average, this is the metric we average across. And so the database, as I said, is a bit of a meta-analysis across these 5 projects, but behind them sits a, team of people that has been thinking and preparing for these experiments for a long time. And that's all we want to, or that's what we really want to share and talk about today. To that end, we will be hearing from these projects who will provide a brief overview, talk about illustrative examples from the database and takeaways, and share some implications for the future. And with that, I'll hand it over to Adam, and I'll ask all of us others to go off camera.
All right. Thanks so much, Anna. Really happy to be here and sharing some of our contributions to this MRV database with you all. This schematic, these very nice illustrations were put together by Carpenter C. I love these, by the way. And this just gives you an overview of our site. So we're probably the most offshore project that's represented in this database. You can see the location of our field trial in the orange dot here on the left map. The little corner of land is the very corner of Cape Cod, so that's Provincetown there. Our dispersal ship left from the port of Quincy, which is marked here, and generally our survey area is outlined by this um, brown circle here. We were very interested in understanding the effectiveness and environmental impacts of ocean alkalinity enhancement in the near field, and actually through the various conversations we had with the EPA, ended up including the ultra near field or ship wake monitoring as a big part of our monitoring efforts. So you can see here on the right-hand side, we had our release vessel um, and a research vessel that was trailing very close behind the release vessel in the ship's wake that had a lot of real-time monitoring that we were doing alongside. So some of this is represented in the database as well. So we're basically considering, the ultra near field as the ship wake during the dispersal itself, and then the near field as being this patch of alkalinity that we established and then monitored with a research vessel for several days after the dispersal. You move to the next slide, please. Um, so like I said, our key motivation was to evaluate the effectiveness and impacts of ocean alkalinity enhancement. We used a dissolved alkalinity product, sodium hydroxide, for this because we were very interested in, once alkalinity actually makes it into seawater, how does that take up CO2 from the atmosphere, and what are the impacts of the pH response alone? And so our measurements really reflect that sampling, that monitoring approach. So we were really interested in all of the suite, as many dissolved quantities as we could measure, um, total alkalinity, partial pressure of CO2, pH, et cetera, other oceanographic things like nutrient and turbidity. We had a whole section on phytoplankton monitoring. Um, Other physical characteristics like salinity, temperature, et cetera. And these really were serving multiple purposes. So not only for the monitoring and quantification itself, which is, I believe this is the bottom bar here, but also just feeding into environmental monitoring, so permit compliance, et cetera. And then also comparing our observations to high resolution ocean models. So the model validation piece was a key thing, and obviously a big thing for developing monitoring, reporting, and verification strategies. I'll just note here, we also had protected species observers on board during the dispersal. Through conversations with the local fishing community and industry, we actually added on specifically sampling for lobster larvae using Newston net tows, which is not represented in this database. And another flag I'll add is that we did, and we relied very heavily on rhodamine, which is a fluorescent water tracing dye that was very helpful for us to unmix the physics of water mixing and spreading from all the chemistry effects. It was also very critical to let us basically exactly establish when we were in this alkalinity patch versus when we were outside. Obviously, this isn't going to be something that could be operationalized in terms of every alkalinity enhancement deployment, but it's very, very critical, and it's not listed on here. So just wanted to flag that. And we can move to the next slide. Um, The near field really does represent a really critical area for us to monitor. A lot of the processes that happened that ultimately set ocean alkalinity enhancement efficiency and its effectiveness at taking up carbon dioxide from the atmosphere are happening in this near field and the ultra near field. And we thought it was really critical to target that area for a lot of our monitoring. And I'll just flag, right, even air-sea gas exchange, a lot of it may happen much farther afield, but it's the same general process, right? It's the same wind speed parameterization and the same gradient in air to sea carbon dioxide concentration that's setting the air sea flux. And that's the same exact process, whether that's happening in the near field or the far field. So the biggest signals are in the near field. So we really wanted to focus on capturing those and seeing how well our models are doing at reproducing those signals. Um, um, we had a whole lot of platforms. So in addition to the number of parameters here, we were measuring this on the ship. On several of these were measured on gliders, on Lagrangian drifters. We actually had some remote sensing measurements as well. What this allowed us to do was assess, just how redundant and intercomparable these different sensors and platforms were in terms of capturing the signal, and give us a sense of how sensitive these various sensors were. The nice thing is that because we did all this sampling, we actually are able to quantify and measure both alkalinity enhancement and CDR signals. And I'm hopeful that this will really push innovation and build trust in MRV. And we can go to the next slide. Rhodamine was very critical for us, so I just want to flag that as being very important, some sort of physical tracer of mixing. We really want to make sure that these monitoring approaches can account and quantify both alkalinity and carbon dioxide. Both of these things are really critical to keep track of. I'm really excited to see how this database can improve community input into the next generation of MRV requirements and standards. And obviously, things are very spatially different and project specific, but I'm hopeful that efforts like these can help to build some common ground for how to move MRV forward. Thanks.
Thanks, Adam. Over to Steve.
Hi, everyone. I'm Steve Romanello. I'm the director of geochemistry with Vesta. I'm going to talk to you a little bit about our Duck, North Carolina project today. So this is a project where we placed 8,000 tons of olivine sand, approximately 1,500 feet offshore and about 25 feet of water off of Duck, North Carolina as a series of nearshore berms. And the purpose of that trial was to allow us to see how olivine interacted and dissolved in situ, but also how it spreads, how it moves, how it interacts with benthic ecology and organisms that are living there to make sure that it's safe. And so if you could go to the next slide here. Um, One of the first things I want to touch on is if you don't sort of work on and think about olivine all the time, there is a narrative out there in the literature that's talking about silica dissolution in the water column, the idea that you would like sprinkle these particles off a boat in the ocean gyre and they would sink down through the water column and dissolve. That doesn't really work, and that's kind of an idea that we wish would go away. And the reason for that is even the half-life of a 1 micron olivine particle is about 140 days. And the time scale for a particle like that to sink out of the ocean mix layer is only on the order of maybe like 1 to 12 days. And so sinking is much faster than dissolution. This sort of approach doesn't work. What we are talking about today is an approach where the olivine is actually sitting on the seabed and mixed in with the sand. So this is very much a benthic approach. It's actually not that different from terrestrial ERW, where you're putting olivine or basalt powder into a field. It's just our field is underwater. And instead of rain and downward infiltration of groundwater, we're really thinking about the diffusion and the advection of products from the seafloor back up into the water column. Next slide, please. And so because of that, like MRV methodologies are very diverse and tailored to the specific technology and use case. So we just heard about a technique that's really focused on the ocean surface and tracing air-sea gas exchange as you release sodium hydroxide into the surface ocean. We're really thinking about what's happening mostly at the sediment-water interface. So olivine dissolution releases huge amounts of alkalinity, but it does so slowly over a very wide surface area. We don't really have a point source. It's a very broad, diffuse flux. We don't really have an impact on the water column chemistry at a measurable scale. We think that actually is a feature, not a bug. It makes the technology potentially ecologically safer because we don't have these extreme pH perturbations, even in the ultra near field. So even 1 centimeter above the sediment water interface, the change in seawater chemistry for a pilot scale project is less than 1 micromole per kilogram alkalinity. It's sort of within measurement error. You will see measurable changes in seawater chemistry for larger projects, climate scale relevant projects, but those projects have to be very large, probably greater than 100 million tons. And so Vesta is a little bit different from the other projects that we're going to be talking about today. For us, what the near field really means, the ultra near field really means, is pore water, the water between the grains and the sediment. So the sediment water interface, the boundary between what's going on down here and that flux into the water column, that's really our outfall. The sediment water interface is the end of our pipe. And that makes this a little different from other technologies in the database. So it's useful to think about that when you're looking at how our technology is represented in this database. Next slide. So what I want to talk about, kind of one thing you can see really clearly in the database is Vesta uses a before-after control impact, or a BACI statistical design. And you see that reflected really clearly in the data. So what a BACI design means is that you're measuring at all of your sites during a baseline period. You're measuring all of your sites after the application of a material, and you're also keeping control sites and treatment sites as you go along. So you've got all 4 quadrants covered. And that's really useful because it allows us to separate impacts that are directly due to olivine placement, whether those are good impacts like changes in pH and carbon dioxide uptake, or potentially negative impacts due to potential impacts on ecology or something like that. And it's been a really useful approach for telling what's a seasonal or a long-term variability kind of change versus something that's happening directly because of our project. So if you look at our project, what you'll see is that the fraction of each measurement type is very consistent among controls and treatments because we're doing the exact same thing at all of these different sites. And the idea is to make sure that we're making tight comparisons between control and treatment. Another thing you'll see about Vesta is that we place a lot of emphasis on monitoring benthic ecology because that's where organisms interact most intimately with the olivine sand. Next slide, please. And in terms of an outlook or where we think this is headed, we've been really happy with the duck pilot. We think the data is coming along really well. You'll actually see the one-year report, which should be released here pretty shortly. There are real signals that are measurable in the environment that are clearly distinct, but the precision on those signals is limited by environmental variability, and the cost and effort of acquiring in situ data is high. And so in the future, one of the things that Vesta is planning to do is to combine both field data alongside more laboratory and outdoor mesocosm testing, both to reduce the variability in the measurements, reduce the cost, and also increase the measurement precision, which is very important if you want to be able to sell carbon credits that are accurate and precise. And so this is baked into the new MRV methodology we're working on with Absolute Climate. One of the things I think this database is potentially really great for is comparing the time and the cost of various field-based open system MRV approaches. We think at Vesta, we think that the next frontier of MCDR will be a focus on how to continue doing great high-quality science at MRV, but to bring these methodologies down to a commercially viable price point. So right now, everyone's spending maybe $500 or $1,000 a ton on MRV. We need to get that price down to about $10 or $20 a ton if we want to be successful as a discipline. Thank you.
All right, my turn. I'm Mallory Ringham. I'm a chemical oceanographer leading ocean sciences for AbCarbon. And the project that's shown on the screen is actually our second in-water type of MCDR test. We originally started working at Pacific Northwest National Laboratory about 30 miles down the road to our east in Sequim, Washington. did a variety of different laboratory and field studies there, and then moved out to this field site in Port Angeles, Washington, to build out a research pilot. So what you're seeing on screen here is an on-land facility, which includes desalination, electrochemistry, various mixing tanks, a pre-existing pier structure, and then on the far right side image, there's a little red barge, and that's our intake and our outfall for alkalinity. So you can think of this project as, in some ways, a very near-shore, very coastal version of what Loch Ness is doing, sustained. So we operated for about 6 months, typically releasing alkalinity during any business day throughout that period. And we recently wrapped this project at the beginning of this month. So what we're doing is we're producing the alkalinity that we're releasing. It's basically an aqueous salty sodium hydroxide, and we get that source by taking in salt from seawater, concentrating it, running a voltage across it to split it into acid and base. The acid is removed, and what we're left with is a combined base and seawater signal. So we can go to the next slide. A couple of things that I want to really highlight in this database that are interesting are some of the ways that private industry has invested in the science, because there's often a narrative that this is maybe something that's challenging for MCDR as a field to overcome, given that the oceans are a commons. There's a number of different measurements that we have to make as a business to operate, and those are involved with regulations, permit compliance, carbon crediting, keeping this type of an MCDR industry up and running. But there are also oodles of voluntary measurements that we make, and often those lines can be a little bit blurry. So something to think about as you're scrolling through the database is that things that are required, who are they required by? That may not always be clear. And things that are voluntary, does that really mean that we could take them or leave them? And what does that mean at different scales? So as an example here, Project Makoma operates under the first MCDR permit using the Clean Water Act. We have a pollution discharge permit that allows us to use a mixing zone where we dilute our alkalinity. We make water quality, carbonate chemistry measurements, things that have to do with some of the models that we're using on the requirement side. But we also do environmental surveys, biological studies. We've brought in external researchers from a variety of different independent universities and laboratories to work around this site. The other thing I want to mention on this slide is that MRV means different things to different audiences, and it means different things to us who are represented in this database. So when we first went through this exercise of providing carbon to sea with the types of measurements that we're making, I think we all kind of lumped them into different categories. What do we consider conditionally required versus voluntary? What do we consider to be measurements around an MRV, which could mean anything from just getting to the carbon story or looping in more and more of the environmental factors. You can go to the next slide. Another important factor here is that each one of these projects is very different, and often pilot scale projects really trade off what you can see and what you can't. Project Makoma is very local. We're diluting a lot of alkalinity over long periods of time, but we still have a measurable signal between centimeters and meters from our outfall. And so when we think about things like model validation, we're often thinking about that extreme near field where we have the most likelihood of actually being able to see something in the water. But we also think about regional model validation, which is out of scope of what we can do. We adapt regional ocean models that are existing, like the University of Washington Live Ocean Model. Another thing is you'll find in the database that I represented are measurements that are quantification based, very low compared to some other projects. And this is because it's really hard to see direct evidence of CDR. We were able to capture a CO2 influx into seawater under very, very specific conditions. Next slide here. The other thing that I want to talk about a bit is how we make choices. And in our case, we really relied a lot on community input. You'll see that most of our measurements are based across our mixing zone, which you can walk across on our pier. And they're also targeted to the eastern side of our pier. That's where our nearest neighbors are, the yacht club next door. That's also downstream from our site during ebb tide, which is when we release most of our high pH alkalinity. So there's a lot of different factors. Happy to talk more about what that looks like. I'll stop there.
Okay, cool. I was lucky to go after Mallory, which is convenient because she made a lot of really good points that I don't have to make now. So thank you, Mallory. My name's Will. I run the science team at Planetary. Many of you on this call are probably aware of our project in Halifax, Nova Scotia, in Eastern Canada. That's the Halifax Harbor broadly on the left, and our site is a coastal outfall delivering mineral alkalinity and taking measurements across that near field, 50, 100 meters away, and then all the way across the harbor. Next slide, please. Thank you. So I'm just going to touch on a few basic points that came from this database. Interestingly, when you look at this, you can see the proportion of ship-based measurements is very high for our project. That's because compliance requires a lot of bottle measurements, and bottles are often taken from ships. And so this creates an environment where you've got questionable on overly, but expensive and time-consuming processes. It does reduce incentive to improve sensor technology. We experience this. We can't, we have to prioritize the things that keep us compliant. But there's also a big fixation for compliance measurements on third-party accredited labs. Even though those labs are overly expensive, have often poor methodologies for what we're trying to do, and have long turnaround times. So the major challenges there. Just wanted to point that out. Next slide, please. You'll also notice in the database that we're taking a lot of voluntary measurements. I forgot to mention at the beginning, this site's been dosing alkalinity on and off for 2.5 years now. So this is a long project, and a lot's changed. So actually, when this process started of making this database, so quite a long time ago now, things have actually changed since this was done. But when you look at our sort of monitoring scheme, you see we've got these stations all over the harbor, which makes sense if you're an oceanographer coming up with this for the first time. As 2.5 years, 3 years goes on, at 2.5 years of dosing, plus all the time doing baselining, it becomes hard to maintain these stations. So it's hard to cut stuff once you've got a good time series going, but that's the situation you find yourself in over time. Now, it's important. Compliance also requires you to understand the ambient condition further away from your site. So you have to keep some measurements outside your sort of area of influence. And of course, as the scale grows, which ours has by quite a few factors in 2.5 years, the scale or the zone of detection will grow as well. So you got to maintain these. What's not near field today might be near field next year. But all that said, we are scaling back some of this big green bar you see because there's just a reality there for what we can achieve. Also, a quick note that when you look at this database, it's not measuring raw measurements. I know that's what Anna said. So there's a lot of actual volumes of data coming from the pier. It's not represented so much in the database. Next slide, please. So my sort of takeaway here is that we do a lot of work not in the near field, and we do most of our work as a functioning project that is having to be compliant and has to produce carbon credits. A ton of work and effort has to be just getting that work done, which makes it challenging to do things like R&D and quantification and setting the bar higher and higher for MRV. But we are doing that work on top of everything else. So we need to focus on the near field. I think that's been said already. Overlap the difference, compliance and quantification. There's my self-timer to stop talking, and we need to get to a point where the Venn diagram overlaps and we make this easier on the people doing the work. Thank you.
Great. Thanks for putting this together and beautiful figures. Glad to bring up the end of this awesome group. So I'm Jamie Palter. I'm a professor of oceanography at the University of Rhode Island, and through funding from the National Oceanic Partnership Program, we did an opportunistic study of this very small coastal lagoon, an estuary. So we went from offshore all the way right up against the land. And the reason we wanted to study this is because we could circumvent permitting and we weren't putting anything in the ocean. In fact, we were working with a golf course who when they can, put down limestone on their greens and to bring up the soil pH. And that's a source of alkalinity to the groundwater. And then there's this coastal lagoon, which is the receiving waters. We call it a salt pond, Winnipeg salt pond. The receiving waters from the groundwater, it's fresher than the neighboring Rhode Island Sound, which is offshore. But that freshening is only through groundwater. There's no river input. And it's like between 3 and 10% groundwater at any given time. So we wanted to see if we could detect the change in salt pond chemistry in this like little triangular embayment by the golf course relative to the rest of this small estuary after the limestone was applied. And so we made quote unquote ship-based measurements from this tiny boat because it's a very shallow system. Next slide, please. And so what I wanted to drive home was that behind the database, when you see ship-based measurement, it's concealing like a huge number of data points and a lot of work, both in the field and in the lab. And what I think a lot of us are coming to the agreement on is that baselining is really important. Chemistry, especially in coastal environments, is hugely variable. This is just one plot to illustrate that it's the total alkalinity versus dissolved inorganic carbon in our system after removing the effects of different water masses from weekly to monthly bottle samples collected at our different sites. And the scatter reflects different processes, but just a huge amount of background variability, order 100 plus micromoles per kilogram of alkalinity change, which conceals any, most signals that we're looking for. And so, yeah, I think that's what I want to say about this one. I'm happy to share more in questions. And then if we go to the next slide, we also weren't only on boats. We had these very small moorings out there with state-of-the-art PCO2 sensors, partial pressure of carbon dioxide from the Pro-Oceanus, which is also reflected in the database as our sensor-based measurements. These collected measurements 6 times a day. We can get a diurnal cycle, the semi-diurnal tidal cycle is maybe almost resolved. And these are just daily averages that I put on just to show you the immense variability again in this system. So again, even though there's hope because there's so many measurements, discerning any signal from the enormous noise requires either a big perturbation or exquisitely detailed background measurements, and really probably both. And so that was the key message from this one. I think there's one more slide after this that links to the database itself. I guess the project that we did, which we did from an academic standpoint, like baselining and doing natural variability in a system, even a fairly well-studied system, is somewhat novel. Then testing what our sensor and measurement capabilities are relative to that baseline, then looking at what's detectable for a perturbation and linking it back all to this great CDR experiment, which in some ways people have done a lot of enhanced rock weathering on land and have trouble detecting it in the land and in the groundwater. We thought potentially we could see the impact in the receiving waters, but for the scale of perturbation and the scale of background variability in the system, it's really, really tricky. So I think baselining and sensor innovation hopefully will increase the possibility of detecting signals in the future. And the database has been useful to show folks what we did and drive home the challenge for detecting the chemical signals in such a noisy environment. And so this figure shows us the trial percentage of different measurements we took by measurement type. And so hopefully that will lead people to ask questions of how we did it and where we headed. I think that's all. So thank you.
Fantastic. Thank you so much, Jamie and everyone else. I'd like to ask you to come back on camera, please. And I'm going to kick us off into the Q&A with a question that's been on my mind lately. And first of all, I want to thank you all for spending the last year or so. I think it's been more than that, as Will said, putting together this database and also complying with my request to keep this very complex topic and cramming it into very short presentations. I know there's lots more to say about all of your individual projects. The first question I have is one thing that for some of those who have been at the Ocean Sciences meeting, perhaps a couple of weeks ago, heard us talk about in a town hall. One interesting observation, I think, from the breakdown into the purposes on the database is that the quantification shares varies across projects. Mallory already alluded to this being probably also due to different interpretations, but I'm curious if you guys have, additional thoughts what the primary driver might be for this. I think we see much more sort of consistent and similar shares of measurements in the other purposes. Yeah, I'm curious if one of you wants to talk to this and share a bit more about why this might be. Mallory, go ahead. You have your hand up.
Yeah, I'll expand a little bit on what I was saying. So for us, when we release alkalinity into Port Angeles, into the Salish Sea, it can take months for the amount of alkalinity that we release to actually affect carbon dioxide removal for the full packet of alkalinity that we put out into the water. And we only see the actual carbon removal flux at the outfall, but the alkalinity that doesn't immediately cause this air-sea gas exchange continues moving. And so we lose that signal really fast. And so when we measure CO2 fluxes above our outfall, I consider that in near field model validation and not in quantification at all, because the quantification that I care about is this massive carbon dioxide removal that will take time to occur. And there's no way that I'm going to measure all of that equilibration cycle over the project lifetime.
Thanks. So very much related to sort of signal detectability at this early stage, and I guess somewhat driven by perhaps the quantification being a bit more of a research question still. Anyone else wants to, Adam, I see you unmuted, want to share more?
Yeah, I guess I totally echo Mallory's point about essentially this near field CO2 flux and any CDR that's happening in the near field is going to be a fraction of the total CDR. And I really don't know right now at the scale of these projects if there's going to be any way to get at that total CDR number with measurements alone. I think it's going to have to be modeled, and that's obviously what the isometric protocol states is the way to get the total CDR, right? So that it is through model differencing between a control run and an ocean alkalinity enhancement run. I will say though that the quantification rate it also relies on knowing how much alkalinity actually makes it into seawater in the dissolved phase. And that requires knowledge of how much is precipitating out potentially, and how much is actually getting released from the feedstock into seawater in the first place. And those two things, right? It's both quantifying the alkalinity budget and what's actually available for potential carbon removal, and then quantifying the carbon removal itself. And I think these two things are separate processes that require their own quantification. And together, they can provide a CDR estimate, but you can't do one without the other.
Yeah, I think one of the things we've talked about to potentially update in the database in the future is breaking down this quantification term a bit further. In the interest of time, I'm going to stop sharing and answer a couple of the audience questions. And I think we have a first one. I have to scroll back up. I just had it. Shoot. Where is it? Here. The question is what % of data you guys are collecting versus extrapolating? And this person is saying that they were under the impression that a lot of the MRV was just modeling, and they're asking whether this is incorrect. Who wants to take that one? Steve, go ahead.
I'll take that. I would definitely push back against the idea that this is all modeling. And I mean, I think anybody on this call would tell you that, I mean, we're out there doing crazy hard, crazy ambitious geochemistry. We've got teams that live in the field. Listen to the case of Vesta. The Hourglass team lives in the field and works in the field every single day of the month. We've spent over $7 million monitoring this project. We measured pretty much everything that's measurable. With lots of different techniques and lots of different approaches. That doesn't mean that we can measure everything we want, right? So we can't, there are some things, olivine takes years, decades to dissolve. And so as that olivine spreads out, eventually it's going to mix into the native sand at concentrations that don't let us easily measure or track it anymore. There's going to have to be some sort of measure period and some sort of later model period. That's also true for things like air-sea equilibration, which have to occur over, we've got a project that's a couple of acres in North Carolina. The CO2 from that project the air-sea equilibration is going to occur over thousands of square kilometers, maybe the entire North Atlantic basin. And so that's something that you can only track in a model. But the idea that it's all modeling is incorrect. It's definitely being driven by hard on the ground science.
Yeah, I can jump in there and also answer the next one after, unless someone sticks a hand up on this question. So yeah, ultimately I agree with Steve. It comes back to what Mallory, I think, maybe said it. What do you mean by MRV, right? Because there's so many measurements being taken, like measurements, what you all think is measurements. And looking at that graph that was on the screen recently, Jamie, I think a lot of Jamie's data is focused on understanding quantification. It's a huge amount of PCO2 data, pH data, alkalinity data. We're all collecting that data. It's a question of whether that sensor data is making its way directly into quantifying the carbon removal, which is a different thing. And it's very, very hard to say a pH in the water of 8.6 somehow makes its way into a quantifiable removal, even though you know from all your other measurements that 8.6 is indeed higher than the background, so it's having the desired effect. But that's a very different thing than actually saying this is how many moles of the carbon you've taken up. So it's a challenging thing that there are measurements and models involved, and I would push back against this kind of the notion of it's all modeling because that's just fundamentally not the case. Onto the dissolution question. Yeah, so that is what we are talking about what I'm talking about when I say the roadmap to a more, a bigger focus on quantification is trying to understand how to do that in situ dissolution. What is the approach there? We have a lot of ideas and we're testing that out now. Alkalinity, paired alkalinity measurements is something colleagues at DAL have presented on in a few different forms. Folks probably have seen that. That's one approach to seeing how your mineral goes from starting out largely particulate. At the moment it leaves the pipe, and moving towards a more dissolved phase as you get further from that pipe. So you can do a swath of measurements to understand that and actually measure it. Again, the challenge is this material is dispersing in 3 dimensions, and you cannot capture every particle. And so how you create that mass balance that Adam talked about, that alkalinity mass balance, is not simple, but it is something we are working on. So I'll let other people jump in now.
If I could add one thing to what Will said that I think for me is how I think about it in my head, which is for any ocean alkalinity enhancement, like step 1A before anything else is you have to prove you added alkalinity. And I don't think anyone would trust a model that you did that. So you have to show that something has to be measured somewhere. And so step 1A, add alkalinity, show that you did it. That's measurements. Then steps 1B through 99 or whatever it is, at some point, to get all the way to a CDR estimate where the ocean takes up carbon dioxide, you're going to have to pass the buck to models because it, like everyone's saying, it happens over large space and timescales at very, very high dilution rates. But I think the reason I want to jump in also at this point is that step 1A about proving that you add alkalinity for mineral-based ones, I think it's very important to show that you have dissolved the feedstock and really understand the timescale of dissolution, the completeness of dissolution, and its resistance to secondary precipitation in the environment that you're in. And so in our project, Hongji Wang is one of my co-PIs, and her postdoc, Teresa Schwimmer, are doing some experiments to look at that. And I think a lot of people are. I think it's a really important high priority task to make sure is going right for mineral-based approaches. So thanks.
That's a great segue also to the next question. And maybe Will, Steve, you want to piggyback onto that answer, which was about how you are measuring feedstock dissolution for mineral projects. And yeah, if you're measuring this in real time or deriving through theoretical estimates.
Yep. We're definitely measuring it in real time. The one caveat I will say there is that we're not necessarily directly measuring like the dissolution of an individual grain. What we're really tracking is the net flux of alkalinity and DIC across the sediment water interface. So we treat the sediment a little bit like a black box. So we're combining olivine dissolution, secondary mineral precipitation, calcium carbonate precipitation. We don't actually try to pick those apart individually in our MRV approach. We sum them all together and we intrinsically measure the net impact of all of those, which saves us from having to try to needle out each process mechanistically. And we think that's a better way to go, to do really high quality MRV without having to chase your tail down 1,000 rabbit holes. And then you want me to cover questions on sort of cost and scale as well, Anna?
Perhaps if Will wants to add something on the dissolution measurements first,
Sure.
yeah.
Yeah, I touched on it previously in terms of a few different approaches. We are, in the field testing now in terms of a way to do it in the field. I think some of the work that collaborators are coming to town to keep working on that question, whether it can be done with a combination of sensors and ship-based. But again, keeping whatever that roadmap is, keeping it realistic in terms of something that you can actually do more than once and without breaking the bank. But at the moment, yeah, we're limited to essentially doing this in a lab-based system and using those dissolution rates to inform the models on how they should dissolve particles. Completing the circle there, of course, will be testing whether the modeled outputs of that dissolution match the size of the perturbation we're measuring in the field. So that's the other side of the work, right? If you're going to tell a model how things are going to dissolve and trust that, you need to then come back and say, okay, the model says the perturbation is going to be this. Are you seeing that level of perturbation? But then you look at Jamie's data and you have to remember that that's a lot easier said than done because of the messiness of the system itself. So again, these are all solvable challenges, especially as sensor technologies improve. But that was my last slide that I kind of rushed there. Is like that needs to be the focus now. And I think everyone's kind of saying that over and over. So don't need to reiterate it.
Great. We have so many questions in the chat, and obviously we won't be able to answer all of them, but I'm trying to merge a few. Steve, you already alluded to it in your slides. There's a lot of chatter about sort of cost and innovation and the need for optimal observation futures. So I'll try to merge these into sort of a joint cohesive question. You all talked about sort of currently, doing a lot of R&D, requiring to take samples, a need for sensor innovation, etc. Where do you see the future of MRV and sort of viable cost moving towards without losing track of your, I guess, ideal observation futures? And what might that future look like? Where do you see sort of the real, opportunities for innovation?
Sure. Well, this is a topic I've been eager to talk about a lot lately. I think it's broadly true. I don't want to speak for everybody here, but the current level of science and the detailed sets of observations we're doing make it almost impossible to sell carbon credits at a profit at the current scale. As I said, like for Duck, North Carolina, we're spending about $700 a ton on measurements in science. So that's not affordable and scalable for large scale climate relevant MCDR. We think the answer to that is a combination of things. We don't think you can really do less science than we're doing in Duck. There's nothing you can really skip or delete responsibly. We have to be doing at least that much science. There may be advantages in sensor evolution, but a lot of times you end up trading a very expensive piece of hardware. And the ocean is very cruel on expensive pieces of hardware. Things biofoul, you still have to go out once a month and clean it and calibrate it. So you don't actually save a ton of effort by using automated sensors all the time. A lot of times you're just trading one kind of labor for another kind of labor. Where we really see the main cost savings is through project scale. And so it's not so much about reducing MRV cost as it is increasing the total number of credits, right? Because it's cost divided by number of credits. And so if your project gets bigger and you're doing either the same amount of science, or maybe you're increasing your MREV effort 2x every 10x in your project scale, you bring down costs that way. So continue to do about the same amount of work divided over a larger number of carbon credits. And so if you're, if we're at $700 a ton right now, and you move to a project that's 100-fold larger, so 8,000 tons to, let's say, 800,000 tons, now you're down to $7 a ton, or maybe $14 a ton. And that's how you kind of bring down cost and scale. So we think that's kind of probably the medium-term future. I think in the long-term future, there's lots of discussion about, eventually we're going to know and understand these projects well enough that we can use mostly models for these approaches. I do think that's probably true. I think that's relatively far in the future, maybe 20, 25, 30 years in the future. There's a lot of stuff we really need to learn and understand, and I think there's going to be a high burden for observations for quite a while into the future.
And perhaps a woven in question for the others to sort of respond to as well, as you're thinking about the future and also the need or even possibility for standardization. Steve mentioned that the cost of MRV will come down if there is more credits, but I think there is also arguments for not increasing the number of credits necessarily, as there also still is a number of uncertainties, right? So how do you all think about sort of making sure the science becomes clearer and we learn about the possibility of quantification at these sites, while also maintaining sort of rigor and not overselling credits from any of these projects? Mallory, go ahead.
Well, so the first thing I'd say in response to that is right now there are very few buyers for carbon credits and even fewer in the marine space. And those who are working in that space generally have expectations of transparency and data. So you'll see this in Frontier, in Microsoft, in isometrics protocols for how we're doing a lot of this work. And that if it's environmental data that someone could come up to the site and collect on their own, it should be in the public domain. So that's something that I just want to make sure is visible to folks. And I think I'll leave the rest of the question for someone else.
If someone wants to. Maybe otherwise, sort of, taking it one step further. One of the folks in the Q&A chat have mentioned that, as many of you said as well, your projects are all quite diverse. And so maybe closing thoughts on opportunities, next steps, and how much we can really compare the MRV approaches across these projects. Are they, similar? Can we draw conclusions from the five of you, or are we talking about apples and oranges, so to say? And what does that say about our possibility for standardization in this field? Maybe Adam, Will, Jamie, we haven't heard from you on these questions. Calling you out. Jamie, go ahead.
Sometimes I think any 2 days at the same location in the ocean is like apples and oranges. 2 different locations at 2 different times, like, I don't know, pianos and thunderstorms or something. Like the ocean is so variable. And so the thing that we have in common is understanding background variability, whatever it is, measuring a perturbation relative to that background of alkalinity, DIC, hopefully CO2, but measuring that is a formidable challenge. So those are the things we share. I think we'd all love to see an alkalinity sensor that can be autonomous, low power, high precision. That would be game changer. I bet we could come up with 3 or 4 other things we agree on. But then in terms of uniformity across sites, it's just the ocean's always changing. So that's just the big limitation.
I guess I'll jump back in on that. I would say that for me, the strength of this type of database exercise is not in comparison, it's in knowledge sharing. So someone can come to me and say, why did you use that sensor and why did you put it there and would you do it again? Those are easy questions to answer that can help drive the right ways to do science going forward. And this is a very small and very collaborative field, even if these projects are not similar in the way that they are operating or in the locations. There's a lot of different things that we can learn from each other. For example, most of the MCDR field operators have talked about secondary precipitation in the last month or so, so there's a lot of different advancements that we can make that don't have to be comparison based, because each one of these processes will be not only responding to the geochemical differences from site to site, but also to social pressures, permitting, regulations, like all of those things have a major, major impact.
Mm-hmm.
Go ahead, Steve.
Sure, I can comment on this a little bit. I think even though I think one of the things that the database shows are some of the differences between all of our approaches, and that's certainly true. Everybody's putting alkalinity in the ocean a slightly different way. And so the details on exactly how you measure it in the near field and the geometry of your system is a little different. But in another sense, ocean alkalinity enhancement, all of our approaches are nearly identical in the sense that we're all adding a source of alkalinity or removing CO2 from seawater. So you're really just looking at adding or removing DIC and alkalinity, basically from a point source or from a field, a small piece of the ocean. That's all everybody's doing. As long as you track DIC and as long as you track alkalinity, everything else is identical. And so there's actually a huge amount of similarity between all the approaches. I tend to see the MCDR MRV space is very simple and very similar between groups, although the tactical details of how you get there are different.
Adam, go ahead.
Yeah, I just want to, I think actually, a big common thread that I had heard that I don't think I had ever heard sort of come out very clearly is that I think we're all converging on the near field being a very important area to study. And that's actually not really been the point that's come out of the literature, the academic literature that's on ocean alkalinity enhancement right now. I mean, a lot of that literature is on this is happening over a huge area, very dilute, very diffuse, like you're never going to measure it. But actually, a lot of the key research and important processes, including the same processes that are happening out in the middle of the Atlantic, are happening right there at the end of the pipe. And that's really the critical thing to understand to really set what's happening downstream. So I'm really happy to hear that coming out in this webinar, and I hope there's more and more focus in terms of research. I'll also just say, like to Steve's point, right? These data sets, there are 5 projects here. These data sets are so valuable, and I would love to see more data sharing and getting this data open and out there for people to get more eyes on it. And also, there's 5 of us. There's a lot of people working on ocean alkalinity enhancement in general. I'd love to see more people doing it. Like get out there, put it through the paces and try to get more projects in the water, because that's the way that we're really going to learn more and grow this community in a way that moves the whole field forward.
Will, closing comments, and then we're at time, and I'll close this off.
Yeah, I mean, Adam summarized it well. I think I don't think one sensor is going to do it. I think that we're going to be able to come up with approaches that are maybe a little bit project specific, but maybe not, of how we get to the point that we already talked about in terms of near field and measurement approaches. we can figure out a way to do that, and that'll be a big step to sort of unlocking this. And it's not going to be you're not going to be quantifying the carbon removal every second. That's what the models are for. But you can get to a point where you got your confidence level up high enough that everyone's comfortable moving forward and scaling.
Great. Thank you. Yeah, I think we're at time, and so I want to use the opportunity to maybe recall some of the threats, despite the projects obviously being different, being in different locations. I agree with Adam. This need for near field really, I think, came out strong in the webinar, and was one of the sort of big takeaways for me also when I looked at the data at first. I think there's a big opportunity and also a caveat that defining these zones, the outfall, the near field, beyond near field, was somewhat awkward across these projects. And rather than thinking about these zones on a distance basis, I think what really we share today is that it's about the processes that you're trying to sort of detect, and the role that a specific region is playing in a project. So really excited to work more from that end. I love the thread on sensor innovation, understanding really how the right parameters will be identified in the future. I think that's a big task for the community at large. And also really we wanted to highlight with this database also that MRV is many things. It is not just quantification. It's about model validation, it's about compliance, it's about environmental monitoring, and many of these measurements that all of you are taking are done for various purposes. And measurements and models sort of really have to come together to enable this. I'll have to unfortunately close us off, and we have so many questions that we probably will be sharing, and we'll figure out how to perhaps make some information there available. Thank you everyone for joining us. Thank you to all of you for going on this complex journey of this database. I'm looking forward to expanding it. We intend to update it, improve it. If you have any feedback on that end, you can email us at feedback@carbon2sea.org. And I think I can speak for all of the panelists here. If you have questions about their projects, about how their project is presented in the database, you can reach out to them. Yeah, I think you know how to find all of them. If not, again, reach out to us through the email, and we'll forward everyone. And sorry we couldn't cover more questions, but yeah, it flew by. Thank you so much, everyone, for taking the time. All right. Have a good day.
Thanks,
Yeah,
everyone.
thank you, Anna. Yeah, bye-bye.